So how many people use Postgres in production right now? That is within shouting distance of 100%. Yes. Wise decision, everybody. So what I'm going to talk about is specifically new features that were introduced in Django 1.8 to support Postgres in particular. Needless to say, given the name of my company, this is not a very database agnostic talk. So the MySQL and Oracle people can go, take a nap. It'll be fine. I'll let you know when I'm done. So the one thing I will talk about briefly is 1.7 introduced native migrations. How many have switched over to the new migration architecture? Yes, because they are like the best things ever. How many people have used Alembic? Yeah, and how many people wish they had Django migrations in like every other framework in the entire world? Yeah, they're really neat. But what we're going to talk about, the payload of the talk, as it were, is Django Contrib Postgres, which is a new module that came in 1.8 with all sorts of really cool stuff. So many features, so little time, so I better talk faster. Okay, and of course, I cannot, I did exactly none of this work. Nothing. I think I sent Mark like 2 emails with ideas, and he did all the work, so all credit to him. I'm going to talk about migrations first, though, even though they're not Postgres specific, because they're an enabler for certain other features that we'll talk about, specifically indexing on some of the cool new types that you have available. And they're just amazing. I just had to do an Alembic project, so I'm still have the scars for that. And Alembic's fine, but still. So thanks, Andrew, for that. Just a quick overview of migrations is that the new migrations architecture is built around a sequence of operations. And each operation moves the data back or forward, and it's through its schema migration timeline. There's lots of individual operations, but there's specifically 2 that we're interested in for the purposes of this talk, which are run SQL and CreateExtension. Run SQL does pretty much what you might imagine, is it applies raw SQL directly to the database. It's if we can't figure out any other way of getting this migration done, we use this one operation. And specifically, if there's anything else that you can't do directly, you use run SQL, like creating indexes for the new types. We'll talk about that. This is it from the new module, Django Contrib PostgreSQL. It runs a CreateExtension command. Postgres in 9.1? When did extensions come in? 9.1, I think. Introduced an extension architecture to replace the previous kind of clumsy way we had for introducing new features into Postgres. CreateExtension is the core command that you run inside the database to add an extension. CreateExtension is a Django migration operation that basically wraps up a CreateExtension for you, so you don't have to use run SQL to do it. The reason is hstore, which is a type that is exposed as part of the new features, is an extension. You have to create it in a database. It isn't there automatically in core. One other thing to know about using hstore, and we'll talk about this in a bit, is if you use hstore, every single time you connect to the database, you're going to get an extra query as part of the setup process. So be aware of that. We'll talk about that. So what we get in 1.8 are some new field types, specifically array field, range field, hstore fields, and those are those three. Cool. So array fields. Arrays have been in Postgres since ever. They're first-class types in Postgres. You can declare a field that's an array. If you're an extreme database person, you might call this denormalized. I don't think anyone is quite that ideologically pure about it. And up until now, there were various modules, there are extensions of various modules lying around the internet that will let you grab an array field, have an array field in your models. But the new array field lets you use them directly as part of, I guess, it's a contrib module, so it's not technically core, but you get it when you install Django, so close enough. They map into Python arrays, Python lists. Sorry, I'm an array guy. You can tell how old I am. And there are differences between them. Something to be aware of is Python. Unlike Python lists, PostgreSQL arrays are of homogeneous type, and they have a single type at the time you declare them. So you have int arrays, you have varchar arrays, string arrays. You have a specific type of array in Postgres. So Postgres arrays cannot handle 1, quote A, unquote B, date time, this, that. You pick one type and you stick with it. Otherwise, but they're close enough at analog that what else are you going to use in your Python? The other thing is if you're using Postgres has old school traditional rectangular multidimensional arrays. They are not lists of lists. Individual entries in the multidimensional array can be null. And in Python, they're mapped to lists of lists, but they have to be rectangular. So each individual member has to have, if you have a multidimensional array, each individual member has to have the same size. Okay, so you can declare them using the array field, the array field model field. And what can you do with them? Well, the first thing is we now get a double underscore contains operator. It matches the array field on the left. If the array field on the left contains all of the entries of the list on the right. So that contains that, but that doesn't contain that. Okay, basically useful. And obviously you can have a single value there if you want, as either with or without the list, the in or out of a list. And order's not important in contains. If you want to do the reverse operation, we have contained by. If the list on the right contains all of the entries of the list on the left. So that's not contained by that, and that is not contained by that, but that is contained by that. And again, order's not important to this one either. Okay, that's neat. There's overlaps, which these two overlap because they both have an A in them, but that doesn't overlap because that one doesn't have a D. It's actually the equivalent of double underscore contains or double underscore is contained by, but this way it's a single operation. We also have under double underscore length as len, which returns the length as an integer. So if you imagine the field landing there, that's 2. Note that if you're doing that, unless you've created an expression index, and we'll talk about how to do that later, this will always be a full table scan. It'll have to pick up and rattle every single entry in the table that underlies that model. So you probably don't want to do this unless you've created this index, or it's a very small table. There's also a transform where you can say array field double underscore 0 equals a, which only queries the first element of the array. If any of those the fields do not have are of 0, well, in this case of 0 length, but that index is outside the range of the particular array value, it returns false. It doesn't throw an error. It's probably the more useful behavior. And you can't. There's no direct way of specifying the index programmatically, of course. So you just use a kwarg to build this part. You can also do slices. Do a slice. That's 0 or 1 equal that. Same deal. It always if the slice is invalid for a particular entry, it always returns false. And you can then also keep building things up, like say contains. So you can build these really wild expressions that I'm not sure how much utility they have, but if you need it, there it is. Okay, now everything I've done so far is great, but it's going to do a full table scan. It's going to walk through the entire table, picking up each entry and looking at it, which if it's a 10-row table is not so bad. But the question is, but we want indexes on these things, because otherwise the performance will be terrible once you reach a table of any size. So we just say db index equals true, like we do for any field, and we're done, right? No, sorry. Because anytime you say db index equals true, what you get is a standard B tree index. In fact, this will throw an error in Postgres, because you can't create a B tree index on an array. Any non-scalar type, basically a B tree index is useless. So let's talk a little bit about what we're talking about here. Which is how indexing, what kinds of indexes we get out of PostgreSQL. PostgreSQL supports multiple types of index. In fact, if you want, you can go and write your own. There's an API that you can write a whole new index type. And this is not just a type for a new type you've defined, but a whole new way of indexing data. So if full-text search didn't exist and you wanted to write a full-text search index and had a lot of time and good C programming skills and infinite patience, you could go and write this index type. Thank goodness other people have done this for us. Generally what people are familiar with is B-tree indexes, and when people are talking about this, there's an index on this field, what they usually mean is a B-tree index. I'm not going to go into how B-tree indexes work. That's well documented online, but you basically get them. Their B-tree indexes are really good. They're a very good solution to the problem. They're fast, they're relatively compact, and they provide ordering. You can walk a B-tree index in ascending or descending order. But they do have some limitations. Specifically, a B-tree index requires total ordering. In Postgres, mathematically this isn't true, but in Postgres it requires total ordering on a type. Greater than, less than, or equals all have to be defined on a type in order to create a B-tree index on them. So for integers and floats and strings, that's no problem. You can always compare those types. But composite types and more exotic types like points, arrays, or hstore don't have total ordering, because you don't have greater than or less than. You could define it to mean something arbitrary, but it's not clear that would be very useful. They're not total ordered types, so you can't create a B-tree index. But they do have other operations that you can do on them, like inclusion. Does this array have this value? Key containment, which in the case of if you're in JSON or hstore, you can say, does this key value pair exist in this item? And so for those, Postgres defines two different index types, which are called gist and gin indexes. Again, I don't want to go into the details of about gist versus gin. That's a pretty wild, hairy talk. But gin indexes are used for types that can basically, first level of approximation. If the actual authors of this code were here, they'd be throwing things at me at this point. But let's just say gin indexes are for the types that contain keys and values. If you were here for the last talk and heard about inverted index, that's what a gin index is. That's in fact what gin stands for, generalized inverted index. So if it contains keys and values like arrays, which are all values, no keys, but same principle, or hstore or JSONB, gin indexes are what you want. For types that partition a mathematical space, you can imagine a line is being broken up by ranges, or a plane is broken up by points or rectangles, you use a gist index. The good part about these is you don't really have to understand all this stuff. You know the right syntax, create them, they'll accelerate the right set of operators for you. So that's the good part. So indexing array fields, arrays support gin indexes. It accelerates these operations, contained by and overlaps. It doesn't help with length or slice operations, though. Those are not indexed by a gin operation. We'll talk about what you want to do if you want that. What the SQL looks like is you create it using, if you're used to the standard syntax, you just say @model_paren field close paren. You drop this little bit extra here using gin field, and it'll go away for a while, maybe a long while if it's a big field, and come back and now you have an index. Gin indexes can be pretty large. They're actually a B-tree of B-trees. And they grow both with the number of rows you're indexing, obviously, and how many unique values it has to index. If you have a lot of entropy in your data, if like every row is its own field, the gin index could be relatively large. Gin indexes can be quite small if you, for example, you have an array. You have an array in every row, but there are only 12 unique values across the entire table. The gin index will be much smaller for that. It should be also noted they're not free to update. They are kind of expensive to update compared to a B-tree index. So don't create one unless you need it. In development or in your staging system, experimentally create one and see what kind of speed-ups you get. So if you have a small table, and I don't have the idiosyncratic definition for small, 100 rows, 1,000 rows. 1,000 rows, you're maybe getting into the space where an index could be useful. But if you have 10 rows in the table, you don't need an index. Now, let's say you want to index length. This is kind of a specialized thing. I'm mostly doing this because it introduces the idea of how to do a functional index in this regard. You can create an index on an expression in PostgreSQL. It doesn't have to be a single unique field value. And that's what we're doing here. We say we're creating an index. It's a B-tree index because we're indexing the length of the array, which is a scalar integer, so no big deal, create a B-tree. You notice there are 2 parentheses here instead of 1. The 2 parentheses are the tip-off to Postgres that what we're doing is an expression, not a single value. Postgres's get the length of an array field is array length, and we say field comma 1. That comma 1 is which dimension in the array we're looking at. Again, Postgres arrays are rectangular, so it's a single value for whichever dimension we go. Everything in Postgres arrays are also 1-based, not 0-based, which is a source of endless amusement if you're constantly switching back and forth between Python and Postgres. This is just a reminder that the first element of every Postgres array is bracket 1, not bracket 0. If you want to index slices, you pick the slice you want to index and create an expression field on that. If you're thinking, this seems of limited utility unless I just happen to be querying the array length all the time, you're probably right. But these kinds of expression indexes can be very useful if you're routinely doing queries on an expression, a particular expression. Postgres is pretty smart, and it'll figure out that the query is that you're using this expression in the query, and we'll use the index instead. And oh, by the way, did I mention that they're 1-based? So why use array fields? Now that we've got them, what do we do with them? Well, the first thing is you want to put an array in the database. Frequently, you're presented with an array as underlying data. It's sample data that you've collected, or it's data from an instrument that comes in as an array. So just store it as what it is. I would say the thing I use the most for is a replacement for a many-to-many table. Here's an example of that, is that in your typical, imaginable social networking application, you have things and people like things. Okay. If the way anybody would do this is they create a many-to-many table in the middle. Well, now you have a billion people and 10 billion things, and you have a x times y many-to-many table. Ooh, that doesn't sound very good. Suddenly you have a 2.5 trillion row many-to-many table. That will be slow. So please don't, calling up your DBA and saying, how can I make that run fast? The answer is you can't. But generally, people don't like that many individual items. Let's say 1,000. And that many and a single item may not be liked by that many people. Let's say 10,000. In that case, just stick the array of who likes what and what people like and who likes this in an array, and index that field much faster. Would I actually build Facebook this way? Of course not. You do ultimate limits of scaling, but to replace a really big many-to-many table, this can be a very, very useful thing. Also, occasionally you want to denormalize and store the results of an expensive query. For example, you may maintain this many-to-many table, but keep intermediate results in like the last 25 things someone liked in an array for fast display. Do proceed with caution here, because you don't want to go crazy on denormalization. That can get you into trouble. But that is one very good use for an array field. OK, so hstore fields. How many people have ever used hstore in Postgres? Not too bad. It's funny because hstore, like, nobody knew about it, and now it's obsolete. It's kind of, but right now is the time to go and use hstore. Everybody run out and add an hstore field in your 1.8 application, and then replace it with JSONB. hstore has been around for quite some time. It's a semi-built-in hash data store. That's what the H stands for. It's a hash. It's like a dict, but it can only take strings as keys and values. So it's a single level, string key, string value, any number of pairs. Pre-JSON, it was the only way of storing this kind of unstructured data in PostgreSQL, unless you turned it in, unless you blobified it and turned it into a string or something in some exotic format. But it was the only built-in way that Postgres actually could analyze the innards of. You have to install it in the Postgres database. It's not part of core. If you're on Amazon RDS, it's installed for you. It's not hard to install. It's like on Debian, the standard community Debian packages include contrib, and it's a CreateExtension operation. And contrib.postgres comes with an hstore extension migration operation to install it for you. So you create an empty operation, an empty migration, drop that extension into it, you're done. One thing that I noted is, because it's created, every type in Postgres has this 32-bit number called the OID, the object identifier. PsychoPG2, the interface library inside of Python, needs to know that OID. So every time it connects, once you've installed hstore, it has to send a query over to get the OID. If you're using any kind of connection pooling or caching, including the relatively new connection reuse stuff that Amrik did, you're okay. But just be aware that there's that tiny little bit of extra overhead that is injected in by using hstore. On the Python side, it's represented as a dict. The big rule is the keys and values must be strings. So no hierarchies, no objects, no nothing. Just strings on both sides. It's translated to and from the database encoding automatically as you go in, which means everybody's using UTF-8 in their Postgres database, right? Yes, please say yes. So what can you do? So you created this hstore field. What can you do to it? Well, you can do contained and contained by. It works just like arrays, only both the key and value have to match. We also have hasKey, which matches fields containing a particular key. So if you want to query for everything that has the key tag or something, you can do that. And hasKeys matches fields containing all of the keys. There is a Postgres operation for any of the keys. Right now, that's not exposed on the query set operations, but there's also keys to match the list of keys in the field. It's generally used with other transforms. So you say like keys, filter keys, which gives you an array, which overlaps this. So this is a way of saying, do any of these keys exist in this field? Less efficiently than using the direct operation, but that's okay. We'll get there. And you also get values that works the same way, only for the value side of the relation, of the hstore. For indexing, you create a gin index. This indexes both the keys and the values, so those tokens are both stored in the index. And it accelerates, contains haskeys, but interestingly enough, but not contained by. So, but these operations are accelerated by the index. So why would you use an hstore field? Well, it's great for storing very rare attributes. This often comes up as you've designed your database and everything's fine, and then the business people come and say, like 2% of our customers need this field. And then somebody comes on later and says, well, 0.5% of our customers need this other field. Now, of course, you can roll out a schema migration and add those two fields, which are only used for those customers. But you're starting to get this hint that marketing is going to say this to you a lot. You can, so basically, if you have fields and there's more than one of them, that's going to be null like 95% of the time, maybe just create one hstore field and make life easier on yourself. One thing to remember, though, is null fields do take 0 disk space in Postgres. So you're not actually saving any disk space by doing this, but you may be saving yourself having to do a schema migration every time somebody comes up with one of these new things they want to store. Of course, if 20% of the customers by customer, of course, I mean rows in a particular table, are going to have this field, you're almost certainly better creating a separate relational field for it, rather than going the hstore route. The other thing is, if the user can define new attributes on rows, but you don't want to roll out a schema, have the user modifying your schema. So for example, if you have let's say you have a packaged accounting application that's a web-based application, and you let the user create 5 or 10 or however many fields on their customer records, you don't want to roll out a new schema migration every time some user somewhere says, I want to add this particular tax code or something to this customer. But you could create an hstore field that is all of the user-defined attributes. So that's one. That's a very common and very useful use of hstore. The reality is, in greenfield development, it's largely been replaced by JSON, which does the same thing but more flexibly and has more operations. And you don't have to install it. And we'll talk about hstore later. No, sorry. But there's no JSON field type in 1.8, so if you need hstore right away, there it is, waiting for you. Or you're plugging Django on top of an existing database with hstore, of which there are a lot. Range fields. So Postgres has native range types. They're a relatively new feature in Postgres, but they are so cool. Range types span a range of scalar types. So for example, 1.8 has all those integers in it. Or they can also be exclusive. So this one is up to the bracket is up to and including, or down to and including. The paren is up to but not including. And the default, if you don't do anything else, is down to and including, but up to and not including. You can also omit a bound to mean all values greater than or all values less than. So, and also some types, like within Postgres that is, have a special infinity value. Dates in particular have infinity and negative infinity as valid values. All of this is materialized in Python by a psychopg2 type called range, which is a base type that has various subtypes to handle specific things like integer ranges and date time ranges and date time with timestamp ranges. And by the way, you should always be using date time with timestamp, never use bare date time. So what we get out of the box in 1.8 is integer range and big integer range, 4-bit integers, 8-bit integers, floats, date time, which is with timestamp, thank goodness, and date range. We have contains and contained by and overlaps, which work just the way you'd expect. We also have these fully greater than and fully less than if both the upper bound and lower bounds of the field are less than or greater than the comparison value. So if it's completely disjoint one way or the other, you can match against fully greater than or fully less than. And adjacent to matches if put up together there is no gap between them. Nor there is no gap or any overlap. This is one place where it's important to understand the difference between an open and closed range, because 1.8 open range with the with paren will excludes 8. So, but with a bracket, it'll include 8, and so this adjacent to will operate differently in those cases. So, be aware of that. We have then not less than and not greater than, which work as described. And indexing them. So indexes, range fields support gist indexes, being as they partition a line up into space, which you use just by dropping the word gist in there. It's easy. And accelerates everything we've talked about. Ooh, so that's cool. So why would you use a range field? Well, why not just use high and low and deal with those? Well, here's a really hard problem. So the hotel booking problem. Don't allow two bookings to be inserted in the database for the same room where the reservation dates overlap. You want a constraint violation when this comes in, like a unique constraint violation. How can you do this in traditional SQL? And the answer is you can't without writing a stored procedure. There's no way to express that with traditional unique constraints because everything can be different. No single thing is the two data things you're inserting aren't identical because there could be some overlap. The only thing that would be the same is the room, but you want to have the same room be able to book more than one time. Fortunately, Postgres has a feature that lets you do this. It's called constraint exclusion. It's also relatively new. Came in at the same time as range types. And it's really neat. It's a generalization of unique. You can think of unique as being a way of saying if an entry already exists in this index for this key and I try to put in another entry for this key, throw an error. Constraint exclusion extends that so there's more than one key value, saying basically don't allow two equal entries based on this set of comparison operators, not just equality, into the table. Any index-supported Boolean predicate, so any Boolean operation that returns a Boolean, can be used in this constraint, and they're ANDed together. But there's a catch, which is it has to be a single index. And since range types require a gist index, the index has to be a gist index. But simple scalar values, like the room number, don't have gist indexing by default. So it seems like, oh, great, I just sold you this great feature, and now we can't use it. Fortunately, there is a contrib module in Postgres that allows, called btreegist, that allows you to create gist indexes on simple types. It's an extension, it's part of contrib, so if you're using like Debian packaging, it's there for you. It has to be installed with the database, but it ships with PostgreSQL. This isn't something you have to go Google up on the internet to find. So if you use the CreateExtension migration operation, you can just add it to your database. So how would we do this? So let's we import the models, import the date range field, and we create a booking. Seems pretty normal. And this is what we get out of it. We get the automatically created primary key. We get the room, and we get a date range. Woo, that's nice, not null. And we get a primary key there. So, what you'd expect. We create this extension, which just happens, and now we create a separate index, a separate constraint. So it's, the syntax is add, and then the constraint. And the constraint looks like this. You say exclude, which means this exclusion index, using gist, just like we've done before. Room with equal, date with at this, which is overlap, which is Postgres' overlap operator. So what we're saying here is, I want to create a constraint index, and if the room is equal and the dates overlap, that's a match, and only allow one entry in the entire table, like this. If I try to put another one in and that matches, give an error. People basically with me so far? Mostly up, fewer down, I'll go with it. And Bing, altered. So let's see how this works. So we say, okay, I'm going to create and this is one place where having an open range kind of makes sense because you can think of this as the check-in and the checkout dates. So, checking in on the September 1st, leaving September 2nd, save. Okay, that's fine. Same room, leaving September 2nd, coming in September 2nd, leaving the 7th, save. That's fine. Here's a different room with an overlapping, with exactly the same thing, but that's fine because it's a different room. Okay, but then let's try booking 1, 2, 3 again, but I'm checking in on the 5th, leaving the 9th. Notice that these are nothing's the same. These dates aren't the same, but they overlap this. And so I get this incredibly long stack trace, which I will not reproduce. And here's the interesting part, which is there's a key conflict. So it just won't let you do that. So that's what you can do with constraint exclusion. It's very nice. It finally solves this hotel booking problem. So why would we use range fields? Well, to represent ranges. We probably figured that out. It's more natural, I think, than the high-low pair. And you have more query operations like overlaps and things like that, and data integrity operations available than if you just do this traditional high-low separate fields. So coming, JSON fields. They're not in 1.8, but they have landed for 1.9. These are fields that support arbitrary JSON structures. They're still a work in progress, so we'll see what we get when 1.9 is released, but it looks pretty good. One thing to note about Postgres is Postgres has 2 JSON types, JSON and JSON-B. JSON stores the raw text of the JSON blob, white space and all. It is, in fact, a text type with a JSON type wrapper around it. JSON-B is a compact indexable format. It's kind of like BSON for people who are Mongo familiar. It's not BSON, but it has the same set of design goals. So why would you ever use JSON instead of JSON-B? JSON is a little faster to insert since it doesn't have to convert the data. And JSON, the reason that we have these two features, these two types, is that there are two very dubious features that unfortunately some people rely on in JSON, which is duplicate object keys at the same level, or a stable key order. The spec for JSON does not say these are features, but some people rely on them. And these are bad people and should feel bad, but we support it anyway. This is an okay thing to use if you're just logging JSON and that you don't plan to query extensively. Why use JSON-B? Pretty much everything else. It can be indexed in useful ways, unlike JSON. And the forthcoming JSON field uses JSON-B, so just roll with it. JSON-B uses gin indexing. It supports these operators in Postgres, which are path, key includes any key, includes all keys, includes any key. One thing about indexing is basically only the top level object in the JSON document is indexed. So we don't do deep level any key anywhere indexing yet. That's a feature that's coming in Postgres. You can query nested objects, but only paths rooted to the top level. Why would you use JSON? Well, people everywhere have their uses for JSON. I probably don't have to sell you on it, but just in case, if you're logging JSON data, if you actually want to store something that's JSON, one nice thing you can do with JSON is an audit table that spans multiple schemas. This is a big traditional problem in relational databases. Is you want to have one table that logs auditing for everything, but which schema do you use? It's kind of a friendly way of pickling Python objects rather than use cpickle or something like that. Storing pickled Python objects directly in the database is not, I would call, the best practice in the entire world, but sometimes you just got to do it. And user-defined attributes in rare fields a la hstore. Basically, completely subsumes all of hstore's use cases, I would say. There are admin widgets, which go with the new types. The hstore and JSON widgets are really only good for debugging. I wouldn't put a blog author in front of these guys. And the unaccent filter, which I'm out of time, so just read about in the documentation. And any questions?
There we go. Thank you very much, Christophe. Just sort of leading into where the future goes and our glorious friend Mark and the things that he's still working on. What do you, if you're keeping on top of it, what do you know of that is coming in 1.9 in addition to this? Or if you don't know, what else is in Postgres that is worth wrapping that you think is easy to
I'm feeling a little awkward speaking for Mark because I feel like I'm standing over him telling program this. The biggest thing that, and this is something you can see from is a framework for creating these indexes in rather than having to use raw SQL. That would be super to create this. I know Mark has plans about this, but it is very much a if he gets time kind of thing. Yeah. So I would say that's the biggest, that's probably a 1.10 feature, I would guess, because there's still design work to be done there. If you know of anything that's going to land in 1.9 that I don't, then by all means lay it on me.
Yeah, it is. You've got me on the spot now. I can't think off the top of my head.
Okay, no, that's fine. That was the leading question. I actually don't know.
Check the release notes.
Yes. I've stunned everyone into silence.
Okay then. That being the case, thank you very much.
Pleasure.